Hello, can you hear me? Hello,
Hello.
can you hear me?
Yeah.
Yeah, all good. Okay, so I think I'm going to start, even if we don't have many students here, but since this is being recorded, I think everyone can refer back to it later on. So let me just start sharing my screen. Okay, you should be able to see the slides. If you don't, please let me know. Otherwise, I'm gonna start. Cool. So good afternoon, everyone. The topic of today's workshop is machine learning tools. So we are going to go through a few different tools that are basically, we try to, again, like previous workshop, we try to cover a few tools that are commonly needed regardless of the specific project that you are doing. So the plan is quickly to introduce Google Colab, which we briefly mentioned in last workshop, but in this workshop, you're going to see actually code examples, how to use different machine learning algorithms on a Google Colab. So it might be, we just introduce that if some of you are not already using it, it's a good tool. And the two major parts that we're going to talk about, the major sections, is first some classical machine learning algorithms, which might be a good choice for some of your projects, depending on the type of data that you have, depending on how big your data set is. And it normally is, again, categorized into supervised learning, unsupervised learning, and dimensionality reduction. So we're going to see some examples of those in terms of both an overview of the method and how to do it in practice on Google Colab using scikit-learn package. And then we are going to move to deep learning and talk about the major parts of any kind of deep learning pipeline. And we're going to see an example in PyTorch. So again, if you're going to use deep learning and you haven't used PyTorch before, hopefully this should work as like a boilerplate kind of code or as a starting point to get you running. And why PyTorch? I think we briefly again talked about this in last workshop, but PyTorch has a lot of good features when it comes to different levels of abstractions. It's easier to use. Of course, you're free to use TensorFlow or other deep learning packages. Even some people might use MATLAB, but that's the recommended package here is PyTorch. So if you haven't started using deep learning before a lot, we recommend using PyTorch, which is very commonly used, one of the most commonly used, at least, packages, if you compare it to TensorFlow, which is the other major one. So the concepts are similar, but of course there are differences between different packages. So even if you're going to use TensorFlow, then this should help get your mind basically familiar with the main concepts. So I wouldn't want to spend too much time on introducing Google Colab, but again, if you haven't used it, I think it's a very good tool. So Jupyter Notebook and Colab, what are the differences? What are the similarities? Basically, a Jupyter Notebook is, and you can install it depending on your package manager. If you're using Conda or Pip, installation is easy. There's lots of basically tutorials online on telling you how to install that, but it's normally just running a single command. So I assume installation is easy, but what Jupyter Notebook on the right-hand side is, you can see an example on the right-hand side. The good thing is that you have basically smaller cells, both for writing text and for writing code. And while you're prototyping, while you're testing many different algorithms, many different codes, while you're debugging, it might be sometimes easier to run the codes like line by line or a few lines. You write piece of code and you want to see the results and you don't want to lose the results in memory. It's also good for visualization if you are going to present a code as we are doing here. So we are going to see how Jupyter Notebook helps. And then what Google Colab is basically Jupyter Notebook in your browser. So it gives you the hardware over the cloud. You can access GPUs. I believe it's Tesla K80 with 24 GB of memory. But of course, it's not guaranteed. It's the cloud. It's the free account. You just need to have a Google account, and then using the link, you can get running. So again, using the Colab is as easy as signing in with your Google account, and then the rest is something that we're going to see examples about. So yeah, takeaway message here is that if you want to visualize some code, if you want to do prototyping, quickly check, especially if you're doing classical machine learning, where normally there's a few lines of code, not very complicated project. It's easier to use Jupyter Notebook, basically run cell by cell and see the results. Now the first part, I'm going to introduce a few of the machine learning classical machine learning algorithms, and we see examples of how to use them in scikit-learn. I like this figure, and I wanted to show in the very beginning, in the sense that it gives you a general overview, a big picture of pretty much all the important machine learning algorithms. So it's, of course, it's not comprehensive. There's lots of specific algorithms. There's lots of more branches that are missing here. But in terms of the general bigger picture, you can basically divide all the machine learning algorithms to classical and deep learning, as we are doing here as well. So the top part, if you're talking about classical machine learning algorithms, whether you are using unsupervised or supervised, so it depends on whether you have ground truth labels for your samples in your data set or not. Then if you're doing unsupervised learning, for example, you could do clustering, and in clustering, you have all these different algorithms. And most of them, I believe, are available on scikit-learn. And then dimensionality reduction is another basic area that we are going to quickly touch, and we see TSNE and PCA, sorry, as examples. If you're doing supervised learning, whether you want to do classification or regression, there's lots of different algorithms. In classification, we see SVM and boosting. So this is a bit subjective, whether you want to basically categorize ensemble methods like the boosting that I just mentioned as classical or not, but I would normally classify them as classical because, for example, boosting, XGBoost that we are going to see is based on decision trees, which is a classical method. But you don't need to be too fussy about this. It's what matters is that these are based on your task, based on the data that you have. You should be able to use this graph and see where you fall and what approach is most useful for your task. And around deep learning, of course, we have CNN, RNNs, GANs, autoencoders, MLPs. Again, for example, CNNs are very good for normal use cases or images when you are dealing with images, RNNs where you have a sort of sequence. For example, if you're doing stock prediction, or if you are doing video prediction or video classification. GANs are normally to generate samples. So you could see them where you generate, for example, I have seen a few of you are working on style transfer or working on imaging painting. So these can generate for you images if you're talking about images or other samples. Autoencoders are very good for unsupervised representation learning, where it could be compared with some sort of clustering, because you're basically learning to encode your high dimension data into a lower dimensionalities. And normal use cases where you have images and you want to extract good features so that, for example, you can classify the images. Let's say you have, on the top of my mind, I remember, for example, if someone had garbage classification. So not necessarily suggesting that this is the way to go, but one way to go as an example is to extract features using an autoencoder and then classify those features. And then for classification, you could go back to, say, classical, or you could stick with deep learning. So this should give you an overview of, as I mentioned, main algorithms that are available, and then it should help you. If you haven't decided yet, based on the data set that you have, based on the task that you have. What is the input? What is the output? Based on those, basically figure out which algorithm works best for you. Now, if we want to start with classical machine learning algorithms first, I think it's good to review what is the motivation of using classical machine learning, right? Some people might say classical approaches are normally older. There's newer and better approaches, like a lot of deep learning approaches. Why should we use classical machine learning? But there's still a lot of good reasons why you want to use that. Most of the times, or let's say some of the times, you might not have enough big enough data sets. Again, I remember some of your presentations, you were talking about the small data sets with a few hundred samples. So if you want to learn something useful using deep learning methods, which have thousands of parameters, it's going to be hard with a few samples unless you do some sort of transfer learning or other stuff. But normally when you have less data, when the dimensionality of your data is small, for example, you have tabular data, when you have 10, 15 different features, it normally works better if you use some sort of classical approach. And you would get better results just because that you don't have enough data to train very large networks with very huge number of parameters. And it's also easier to tune these methods. Normally, they don't have too many hyperparameters. Normally, there's 1, 2 hyperparameters. Even with the default values, sometimes you get very good results. They're not very sensitive, and most of them are not too sensitive to hyperparameters. And of course, you don't need very big hardware, right? For some of the deep learning methods, you might need big GPUs, but if you don't have access to them, then you could use classical approaches, and they run quite quick on CPU as well. So the answer to why you want to use, and then the classical approaches that we are going to see in terms of classification, 2 examples, SVM, which is kind of the one of the very first algorithms in classification, and gradient boosting, which is a bit more recent. Basically, they could be kind of seen, from my opinion, to basically one very first very old algorithm and the other one a bit more newer that you could deal with the differences between performances. And in terms of clustering, a good example, if you don't have labels, if you want to extract patterns in your data, a good example is K-means. So when people again, the purpose of the workshop is not to go into the details of these algorithms, but we need to be on the same page. We need to make sure that we have everything on top of my mind on top of our mind, to the extent that we need when we go and see the examples in the code. So the SVM, the idea started with binary classification, where you want to learn a function basically that if your labels are positive, it gives a positive value. If your labels are negative, it gives a negative value. So you could see 2 different basically data points here in 2D, and the idea is that you need to find this function to be able to find a good boundary, a linear boundary. So when we are talking about SVM without any kernel methods, we are the SVM is basically a linear classification method, in the sense that the basically decision boundary that it finds is a linear function of this sort. So if it is in 2D, it's a line. If it is in higher dimensions, it's a hyperplane. But it's still a linear classifier, in the sense that you have some parameters and a bias. So it's a linear function that you learn. And the overall idea, the general idea, is that from the data points that you have, you are trying to find the equation of this line, again in 2D, and in higher dimensions, it's a hyperplane. But in 2D, you want to find this line that maximizes the sum of distance to all these support vectors. And what are they called support vectors? Because these are the closest points to the line, and they support basically the decision boundary, the line that you learn, the parameters of the line that you learn. So you want to find this line that at the same time has the highest maximum possible distance to all of these points. And if you want to do multi-class classification, so that's just to note, that's also called maximizing the margin. So maximizing the distance between the line and those points. It's that distance is called the margin, so you're maximizing this margin. If you have more than one classes, the way to go with SVM is to do one versus rest. So instead of having a single classifier, single line, you will have, if you are dealing with 3 classes, for example, you will have 3 classifiers. Each of them are binary in a sense that there's one versus rest. So if you're learning a boundary for green, you would learn what is the best boundary that separates green from every other sample. So you would consider blue and gray as all gray, as all basically representing a single class. So that's why it's called one versus rest. So it's possible to do more than binary classification. And we are going to see examples of the code as well. But before moving to that, let's see another example of classical machine learning approach. As I said, this is a more recent. It was a few years ago, was the Kaggle competition winner. It got a lot of attention. The idea is very simple. The idea is that, okay, what if you learn, for example, a SVM, the general idea of ensembling is that what if you have an SVM that doesn't perform 100%? Of course, most of the time it doesn't. Let's say it's a weak classifier that performs 50 to 60%. Then the idea is, can you learn another function that basically another classifier that can classify the rest that the previous one couldn't classify? So that's basically the overall idea, that from a few set of weak classifiers, you combine them, you ensemble them, and you find basically an ensemble method that each one of those weak learners focus on the area that the previous one was not performing very well. So if your first classifier performed 60%, let's say, and 40% of the data samples didn't work well, then the second one would focus on that 40% to try to classify those. And gradient XGBoost, it's called in scikit-learn that we are talking about here, or gradient boosting classifier. It's a combination of decision trees and the number of estimators, for example, and the max depth are the important hyperparameters. So the number of estimators tell you how many estimators, how many different classifiers, separate classifiers you train. And in this image, what you should be able to see is that if you have a single classifier here, for example, this red and blue are the learned boundaries. And you could see that there is a lot of, like a few blues here that are not properly classified and one red. And as you increase the number of estimators, you could see that you would learn additional boundaries here, that a few of these blues are going to be classified. For example, these 4 blues are going to be classified correctly using this ensemble. And you could still keep those 6 reds. Of course, there's a limit to how much you can push this. You cannot expect that you add 100 estimators and they get 100%, because these are the problem is that every one of those have their own limitations. In this case, they're linear classifiers, and there is still a chance that no matter how many of those you add, you cannot still get 100%. But most of the times, it gives you a significant boost from using a single classifier. So that was the, we'll see this clustering as well, and then we'll move to the code example. So those were 2 kind of major examples of classification. If you're dealing with classification in classical machine learning, those could be one of the choices that you might want to try and see which one works for your data the best. If you don't have access to ground truth labels, but you want to still extract decision boundaries, find patterns in the data. For example, let's look at this right-hand side figure, right? You could see with a glance that maybe you have 2 to 3 clusters, depending on whether you want to consider this blue part as a cluster. I wouldn't probably do that. So a good decision boundary could probably be this line between orange and green. So let's say you don't have the labels, you don't know these green and orange, and you want to find them. That's where the clustering comes in, and a good example is k-means. So the idea in k-means is that before assigning any labels, let's imagine all these points are the same color, are gray. They don't have any labels. So what you do is that first you need to define the or speculate the number of clusters that you think exist in the data set. That's normally done through prior knowledge. For example, if you know that you're dealing with images of digits, as we are going to see, and you know that you have 10 different digits, 0 to 9. And then that's the prior knowledge that you have, that in your data, you know all your images basically are one of those 10 possible digits. Then that you know that you should ideally have 10 clusters. And the idea is that the similar numbers should be close to each other. Now, how K-means does it is that it iteratively starts with random assigning of the centroids. And what is the centroid is basically the mean of all the points that have the same label. So you randomly assign those points into clusters, and then from the points in the same clusters, you calculate the centroid. And every time, so you start with an initial random initialization, but then you find the closest point to the centroid and assign them to the same class. So for example, let's say that if we have selected this green triangle here as the centroid, then we calculate the distance, pairwise distance of all the points here to all these three centroids, and see which one, each point is closer to which of these centroids, and then we assign them to the same cluster. And we iteratively do that again and again until we see that these clusters wouldn't change. It might be a good idea actually to have a look at a visualization. I think there's a good visualization here at this website. I'll add the links if anyone is interested to play with that. But that in order to see the idea, for example, let's just start with some random initialization, right? We start with these random points. We have all these points. Let's say we already in advance know that we have 3 clusters. What happens first, we randomly assign those points to each of those centroids. And then what will happen is that now we will calculate every single pairwise distance to the centroid, and we update the centroid. And we repeat that again and again. Find the closest centroid and update the centroid. And we will see that as we do that again and again, then there is a point that these centroids wouldn't move too much, or the labels of these points wouldn't change that much. And that's where you can say the algorithm has converged. And now you have found 3 clusters. Basically, you have labeled these points without having any ground truth labels. So that's the idea of K-means. And let's see now some examples of all these methods that we talked about in Google Colab, if my Google Colab works properly. So again, for those of you who haven't used Colab, again, I already have an account in Gmail, but for the first time when you Google Colab, if you Google it, then you would see this welcome to Colab Collaboratory. And if you haven't signed in, then it will ask you for your Google account details, and then you would end up, if you don't have any examples, so I already have a few Colab, you would at least have this welcome to Collaboratory, and then you will see this notebook, and we can play with that. It's basically, as I mentioned, Jupyter Notebook that has access to cloud hardware. So here, let's see the examples that we talked about. Just a random NumPy array to generate and see if, so the good thing again about Colab is it comes with most of the packages that are popular. So you don't need to install any of these NumPy, Matplotlib, scikit-learn. Those are very commonly used. But if you need to install, you could run the commands, I think, with this module line. You could install if there is any packages, but it's very unlikely that you would need some package and it's not already installed. In order to see those examples, we need to have, of course, a data set. In scikit-learn, you could see the list of data sets that are available. There's a few data sets already there. For example, we are here loading the Irish data set, which is I think it's some features about flowers, and then they are clustered into 3 different classes. You could see the details here. You have 150 samples, and dimensionality is 4. We have 4 different features. Or the other data set that here we are loading to work on is the digits, and it has 1,700, almost 1,800 samples of different digits. And These are between, each of them has 64 dimensionalities. There are 8 by 8 images. And of course, there are 10 classes for 10 different 8 digits. So here we are just loading those data sets, and we see an example of the digits. I cannot read this one. It's supposed to be, we should be able to get the labels as well. I think we have the example here. Digits targets. So if you get the targets of the same ID, you could be able to predict the target. That's the image. Let's say print digits what target, and then the index that we randomly selected. Oh, we already had that here. So this is, for example, a 3. You could see the image, and you have the target value as the ground truth. Let's skip this part because we haven't seen that part first. We will come back to that. So the classifier. I think we briefly saw the general structure of how to use scikit-learn functionalities. But to review that, for example, SVM is in the scikit-learn library itself. And then the SVM classifier, it's actually called SVC because we have SVM regression as well, I think. So the way you can use this is you need to first instantiate one instance of that class of SVC, given the parameters that you need. So there are a few main hyperparameters that you could use. For example, C is a regularization that tells you basically it's in inverse regularization, let's call it. The higher the value is, the smaller that the regularization. And that regularization basically decides on how many points in that decision boundary that we decide we want to be lenient towards. We want to be, we want to say, okay, it's, for example, 3 or 4 points. If they fall within the boundary, it's still fine. Let's find a classifier that it's okay that it doesn't classify 4 of them, roughly. So the effect of regularization is that it basically balances between being very strict, finding a very strict line, which might or might not be possible depending on how your data is basically structured and how you want to. And normally it's better to have this regularization. Of course, the value is a hyperparameter, but I think most of the times the value between 10 or 100 regularizes. You could see if you increase the regularizer, then your results. So increasing the regularizer, by the way, here, because the C is inversely related, you need to reduce the C. So when you increase regularization or reduce the value of C, you become more and more lenient, and that's not a good thing. So there's a level to that. If you are too much okay with non-correctly classified points, then your performance falls down. So here we are just seeing 2 different ways of setting parameters. So there is a few important hyperparameters. For example, kernel is another one of those. And the idea of kernel is, and it's by default RBF, there are a few different kernels. But the idea of kernel is, for example, if you have 2-dimensional data, I think we had an example on the slides. Let's look at this data, for example, on the right-hand side. We know that SVM is a linear classifier, right? But this data is not linearly classifiable or linearly dividable, whatever you want to call it. So we cannot find a line in 2D that gives us 100%, whereas on the left-hand side, we could. So the idea of kernel here is to implicitly convert or transform your points here to higher dimensionality, that they become separable. Imagine that you add a 3rd dimensionality here that, for example, your triangles now have a higher value. And if you imagine like the 3rd basically axis is perpendicular to this plane that you're observing. So let's coming out or going into this plane, into this image that you're observing is the 3rd axis. Now, if your triangles are further away from the screen, let's say, and your blue circles are on the screen on the same plane, then in 3D, you could find a hyperplane that you could separate them. That's the idea. So with kernelization, you implicitly transform your data points to higher dimensionality so that they become separable if they are not linearly separable in the original state. Again, most of the times an RBF kernel works fine. The details of those kernels, mathematical details of those, are out of the scope of this session, but it's good to know that these are important hyperparameters. And if you are not getting the results that you expect, you could play with these hyperparameters. And we're going to see how to optimize those hyperparameters as well. So assuming that you have, basically the first step is you want to fit, no assumption. The first step is after you have instantiated that classifier, you want to fit on your training data. Again, assuming that, the assumption is here, assuming that you have separated your data, split your data into training, testing, validation. Now you want to fit your function on your training data. And when you call fit, then your classifier in the background will figure out all those parameters, and it will be stored in the classifier object itself. And you could use the predict function now. Let's say you want to test your classifier and your test data, you could use the predict function and pass the input. So of course, when you are fitting, you need to pass both the X and Y, yeah, input and outputs. But of course, for prediction, you just predict on the input. And we can see here that, for example, when we fit this classifier and this simple data, it is working. So like this is the score, the accuracy that it gets, and it's 78.2. And we could see the result of the prediction and the actual target. So the actual target was digit 8 and the prediction was 8. And the score function here calculates the score on the data that you give. So here we are calculating a score on the training set, but you should of course do it on the testing set as well. So you see every time that you train it, you get a slightly different results based on the random seeds values that you're providing. Full list of hyperparameters you could see there. Those are the major ones that are basically that would change your results significantly. A good way to tune your hyperparameters is, for example, if you have a few of them, let's say in kernel, you have, again, in that link, you could see all the options. I think there's 3 options only, linear and RBF and another one that I don't have on top of my mind, but you could check all the possibilities and pass them as a list or as a tuple. And then basically what grid search does, grid searches over these parameters. So it checks all the combinations, all the possible combinations, and finds you the best set of hyperparameters. And now you see, for example, with the default hyperparameters that we defined here, it was performing around 79. Now, after we run the grid search, we see that hopefully previously it was around 96. So that's how important it is properly adjusting your hyperparameters. And you could automate this if your range of hyperparameters are very large. Then you could also, there's also more basically more smart way of hyperparameter optimization rather than grid search, like there's Bayesian optimization and stuff that you could follow. But normally, if you could see that like classical machine learning algorithms normally are quick enough, so you can easily do grid search. Of course, when you train your model, you need to save it. If sometimes later on you want to come back and basically you don't want to train it from scratch, it might not sound very useful when you have an algorithm that trains in 1 second, but it's very important when you have, you're going to see depending on your size of the data. And also, for example, in gradient boosting algorithms, it takes much longer. It might take a few minutes. So of course you don't want to run that training every time and wait a few minutes. So it's a good idea to save your classifier, and you could use Pickle basically to save your classifier and you load them. So here, for example, we could basically use the pickle.dump, and what it does, it saves your classifier, and you could use joblib.dump and load functions to save them on a file. So pickle.dump gives you, so you could save this S directly using Pickle, or you could use joblib and directly pass the classifier and save or load it. So what is here important? So you can see that we loaded classifier 2 from that S object that we saved as the previous classifier, and it should provide the same results. So if we run it, because we have loaded the previous one, it should give the same results. So it's a sanity check to make sure that you have properly saved and loaded your classifiers. Moving from SVM to gradient boosting that we talked about on the slides. Again, as I mentioned before, the use of all of these methods all of these algorithms is the same, in the sense that all of them are classes. You need to pass the hyperparameters. The important ones are here, and the fit function, always you call it on your training set, and fits trains your algorithm, and the predict always does the prediction. And the score in most of these classification algorithms is accuracy. If it is regression, the score might be something different. For example, it might be the actual loss, L2 distance or something, but in classification, it's accuracy, and you could use directly the score function to get the score, the performance of your method. So now going to gradient boosting classifier, it is part of the ensemble library, and I think we saw the other new thing that we have here is train test split, which is a function that randomly splits your data. So if, for example, here we are using the digits data set, and the data has the input, all the images, target has the classes as we saw, we could pass them as X and Y's and split them randomly based on the percentage. I think there is a default percentage. The percentage parameter, I think, I don't know, on top of my mind, let's quickly check. So these are all the set of parameters, and test size, for example, is you could use directly test size or train size, and then that would define basically the split that you want to do. That was the parameter that I was looking for. So here by default, I don't think what the default value is. Let's see what the default value was. Okay, 25% is the default value. So if you don't set it, it's 25% on the test set. It's always better to set it yourself. For example, let's say you want to keep 30%. So that does the splitting, and then we pass the we instantiate it with these hyperparameters. Random state is for you to be able to reproduce the same results, because it's a gradient-based algorithm. There's some sort of a stochasticity, some amount of a stochasticity, in the sense that if you run it multiple times, you might get multiple different results. So if you want to reproduce them, it's good to pass the random seed number explicitly. Number of estimators is, as I mentioned, the number of different classifiers, independent classifiers that you want to have. Normally, your performance increases as you increase them, but of course, there's a saturation point. So, for example, you might start with 2 classifiers, 2 estimators, and go up to 10, and you see improvement continuously, but then increasing after 10, it might even lower your performance. Maximum depth, because here we are combining decision trees, is the decision tree depth of every single decision tree. Again, this is another important hyperparameter. So the rest is kind of the same as other classifiers. You could see with this kind of hyperparameters, we got 83% accuracy. That's if we reduce the number of estimators, for example, we get 80%. But if we increase that to 50, 80, from 80 to 83, let's see how much we got to 87. Okay. That's why hyperparameter tuning is very important. Again, you could use the grid search that we saw before on the same thing, and you would be able to potentially get even better results at 89%. Of course, this is on training set, right? We haven't even tested. Oh no, that's on testing set, sorry. So the first 500 samples, that's the slicing. The first 500 samples up to the first 5, all the samples except the last 500 are in the training set, and all the samples, all the 500 last samples are the test set. So this is on test on scene set, and on training set it should be higher as well. Let's compare the same kind of samples on a single decision tree. So that's another good sanity check that you are doing it rightly, right? Normally, ensembling methods should perform better. If it's not performing better than a single classifier, then you are not getting the right hyperparameters most probably. So that's a good sanity check. Moving to clustering, again, the overall architecture or the overall structure of running or using those methods is the same. You instantiate them. You need to know which library they come from. So k-means comes from clustering. All these is easy to look up on scikit-learn website. If you don't know the library, I myself most of the time forget the libraries. But then when you find the library, you import them and you instantiate. You could do instantiation and feed at the same time. Important hyperparameters here, probably the most important one is the number of clusters. As I mentioned, most of the time it's a prior knowledge. If it's not prior knowledge, sometimes you might want to try different ones and see what is the overall performance in terms of, for example, the distance between the centroids. So you should be able to see as you increase the number of clusters, you reduce the average distance to the center of clusters, but then that also saturates at some point, which suggests that's the best point of choice for number of clusters. This is another example. So there are many ways, different ways that you can define that, but normally prior knowledge is the best one. If you have some sort of knowledge, what is the structure of your data, which most of the times you should. So you fit that, and then you could check the labels on the plotting, and you could also predict with new data points. So let's say we randomly generated some data here. You see the 0.6 points on the left and right, and we see the left ones, all three are associated with cluster 1, the right hand ones with cluster 0. And then if we try to predict these 2 points, of course, one of them is here, 0 and 0, the other one is 12 and 3, this one's around here. You could see the prediction. They are associated with certain clusters. So that's kind of a quick overview of some of the major classical machine learning algorithms and how to use them in scikit-learn. Is there any questions, or can we move to the deep learning? We are a bit behind schedule as well. Okay, if there are no questions, let's change the topic a little bit to deep learning, and let's first see a few slides. So I would imagine you have higher dimensionality data, a lot more samples, or you're using a public data set and you're saying, okay, classical machine learning is not a good fit. Deep learning, I guess I quickly went through this motivation. Like you have higher dimensionality of data, you have lots of them, you have a good hardware as well to be able to deal with those data, because normally these deep learning methods need a good GPU, otherwise you're going to be too slow. And the good thing is that the functions that we learn are very highly nonlinear. So we saw that, for example, in SVM, even though you could use kernel methods and still deal with nonlinearly separable data, but that nonlinearity by itself is limited to the kernel functions that you're using. In deep learning, you could essentially theoretically learn any nonlinear function that maps with most, no matter how. I mean, in practice, it might not be true, but technically, you should be able to learn very highly nonlinear samples, no matter how nonlinear they are, decision functions, if you're talking about classifiers. In installation of PyTorch, again, if you are already using a package manager, either Pip or Conda, you could head to PyTorch website, and it gives you, I think this is a bit old now, we have version 1.9 or something, but you could select the PyTorch version, your operating system, your package manager, and your CUDA version if you are going to use GPU, or if you want to still run it on CPU, you could select none, and then it will give you the command how to install that. That should be straightforward. Quick review of CNNs before moving to how to train a CNN as an example. So a convolutional neural network is a combination of different kind of layers. Most major layers that you're going to see in many of these CNNs is convolution plus a sort of nonlinearity, one of these ones that you can see on the right-hand side, and some pooling layers, and at the end, some fully connection layers. So this architecture is up for design, right? This is, of course, for a task that we want at the end 10 output for a 10 class classification. So if you want to generate a picture on the other side, or if you want to do segmentation, which is a mask on potentially the same size as the input, then you need to play with this architecture. And this architecture is actually quite old, but the building blocks are the same. So you play with those building blocks, or people play with those building blocks, do research and come up with newer version of networks. We have ResNets, we have ResNext, lots of newer network architectures for different tasks. But the building blocks are still quite similar most of the times. So convolutional layers, basically you extract features out of the input feature maps that you have, whether it's the input itself or the intermediate feature maps. Non-linearities is to basically add non-linearity to make your function to be able to handle non-linearly separable data. And then if you want to do subsampling, for example, your input image might be 32 by 32. But if you do, let's say, only convolutions, if you don't have a strides or anything that reduces the dimensionality, at the end, you might be dealing with a very huge number of variables. So normally people use pooling layers to reduce the dimensionality, and then fully connected layers are the ones that help you to map your final extracted features. For example, here in Lenet, these could be the final features that you have extracted. Now you want to convert them to a vector and map them to your final desired dimensionality. Different activation functions, whether you're using them in the intermediate layers or output layers, it depends on your task. For example, if you have multi-label classification, you might want to use sigmoid. Why? Because every single value will be mapped between 0 to 1. In intermediate layers, people normally use ReLU and leaky ReLU, and those are the ones that work fine. This is a huge topic by itself. So why this works well, vanishing gradient problems and those kind of things, but it's also a bit out of the scope of both the project and this class, because on your side, it's mostly knowing which network is a good fit for you and the application. Most of the times, I'm not saying 100%, but most of the times, sticking to the state of the art should be good enough for your purpose. And knowing that, for example, there is an activation function missing here, which is called softmax. If you're doing classification, most of the times the last layer is softmax. Why? Because softmax converts your logits into a distribution of probability. So if you have 10 classes, you want to say, yeah, out of your network, the output is predicting the probability of assigning to every single class, assigning the input to every single output class. So it's good to know what is the difference between these and why they matter. Coming back to the Jupyter notebook. So in PyTorch, there is lots of pre-trained networks. There's a few different data sets that are available that you need to use. Of course, you don't necessarily use the CIFAR 10 here that I'm using, but that's an example to be able to see the training pipeline. There are different libraries for different purposes. The Torch itself has all the neural networks, everything. Torch Vision normally contains the pre-trained networks, default networks like ResNet, VGG, all those kind of stuff. Transforms is more normally used for pre-processing. We're going to see examples here. So the first step is to load your dataset. Now, here we are using the default dataset of PyTorch, but if you're using your a public dataset or your personal dataset, you need to override this dataset and data loader functionalities or classes. So that's something that we are not going to discuss here. We are assuming that from this Torch Vision default datasets, we can just load CIFAR 10, and we can put this into this path directory that we are assigning, and we want to say whether we are using the training set or the testing set, and if you need to download it or if you have downloaded it previously. So if you are using any other data set, personal data set, you would need to override this functionality. And what it needs to have is it needs to be able to go to this directory, no matter what this directory is. This is for you to define and be able to fetch your data one by one. So that in the data loader, now, whether you have defined it or it's a data set that you're using from PyTorch, the data loader, what it does, it gets that in object of the data set. And you tell basically the data loader what is the batch size and whether you want to shuffle your data, what is the number of workers in parallel. So batch size is, for example, let's say, like here, if you're dealing with images, normally you need to batch your images, multiple of those together, so that you get better performance, so that the gradients that you are calculating are not noisy or not single sample. And normally, the larger this batch size, the better the performance. But again, it's one of those hyperparameters that has a saturation point. It depends on the size of your data set, on the task, on many different things. But of course, having a single batch size most of the times doesn't lead to good performance. Anyway, so you need to define your data set, and then you pass that data set object. You define a batch size, and you say whether you want to shuffle during the training, you want to shuffle your data every time you load, you loop over to whole data. And number of workers defines how many workers in parallel you want to use to load your data, so that your data loader works faster. So you build the data set, or you load a data set if you're using a pre-trained one, something that is available on PyTorch, and then you define the data loader. I wanted to say something else, but no, I think that's it. Similarly, you need to do for the test set as well. So again, here we are downloading the cipher from one of the Torch region's public data sets. We say that this time training is false because we want to load the test set. And now going back to this transform, so it's very important to have some sort of pre-processing minimally to normalize your data and to convert your data to tensors. For example, again, I keep saying images because that's a good example that you might see a lot of good tutorials on, but that doesn't mean you couldn't do with other modalities. Like if you're dealing with text or if you're dealing with tabular data, it's still the same. So in images, you load them as PIL package images or OpenCV images. They're not still tensors. You need to convert them to tensors. In text, you have your own tokenizer. You load it and you tokenize it, and you get some sort of, again, you're using Word2Vec or whatever. You get representation USD. If that's a NumPy array, you need to convert to tensor. So that's necessary. No matter what your data is, you need to make sure, whether here or in advance, you need to convert it to tensor. So this transforms.compose function and the list that you pass defines all the transformations. So here, as I mentioned, minimally having a conversion to tensor and then normalizing your data and passing a standard, the mean and a standard deviation. Here we are having 3 channels as RGB images. So we have, these are not calculated. So of course, these are default values. You need to calculate them based on your data. So this is the standardization that we talked about in the previous workshop. So you generate a list of the different transforms and you pass it to compose, and then this compose makes sure that those are run on every single sample that is loaded before being basically fed out by this data loader object. So that's unloading the data side. So we should be able to load that and see transforms not defined. We didn't find this. So that should be now. If you're doing it for the first time, it takes a few seconds to download and save, but next time it should be available. We have some helper functions to visualize the images. That's not really something that is related to PyTorch. You could use any package to load and visualize your data. For example, here we see the images and the labels: sheep, frog, truck, horse. Again, this was part of the previous workshop. It's very good to check your data set and have a sense of what you're dealing with. Just a quick note, we are at 2 p.m. We are going to probably take this a few more minutes, maybe up to 10-15 minutes. If anyone has any commitments, of course, feel free to leave or welcome to stay so that we need to finish this. So, okay, now that assuming that you have loaded your data, you have built your data set and data loader objects for both the training and testing set, the next important stage in almost any pipeline is building your neural network. Here, because we are dealing with the 10 class classification, was it 10 class? Probably 1, 2, 3, yeah, it's Cypher 10. Cypher 10 is 10 class, sorry. We have Cypher 100 class, I think. So here we are dealing with a 10 class classification. Normally, the way that you define your neural network is this. This structure is very standard, unless you want to do something very complicated. And you need to basically load this NN library that includes all the neural networks, different layers, conv, max, pool that you're seeing here, linear, they're all part of this. And then the NN.functional, normally people give it a name of F, big F, and that has all these activation functions that you want to use. So these are the kind of the minimum requirements. And in terms of how to put the network together, you need to basically define this in your network class, which extends this NN module. And it needs to extend NN module because then that handles all the gradient calculation, all the forward, backward loops and everything. Two main methods that are necessary to be defined is init and forward. So in the initialization, you would define all your layers. You would instantiate, these are all classes. You would instantiate all the layers that you want to use in your network. So here we are having 2 convolutions, 1 max pool, and 3 linear layers. For a list of parameters, again, you could refer to PyTorch, but in conv2d, I think the first parameter is input channels, in channels or in channel. And then the second one is the output channel, the number of output channels you want to have. And the third one is the kernel size. You have other parameters like the stride value, padding value if you want to do the padding. And if you don't, if you set it as a tuple, if you want to have like different kernel sizes for non-square kernel sizes, you could say, for example, I want the 5 by 3 as a tuple. Or if you want it to be a square, you could just pass a single integer and it assumes that's a square. This is the way that you define comms, max pooling. The first one is the kernel size, the second one is the stride. And then for linear layer, you need to have input and output, number of features in the output because it deals with the vectors, and the second one is number of features for the output. So you need to define all these layers, and in the forward loop, you basically define how these layers are connected. So if your input X should go through conv1 first or conv2, this is where you define that. So we say that we get the input, we feed it into first convolution, we do a ReLU activation on top of that, and we do the pooling on top. And then we do that for the second convolution. And then the other important thing here is that when you go from convolutions to linear layers, the output of convolutions, if you're using 2D conv, it's 3D features. You have 2 dimensions for the height and width, and you have a third dimension for the number of kernel sizes or the number of feature maps that you use. And you need to map that into a vector. Here I just assume that your batch size is another dimensionality, but that's always the case. So you have the first dimensionality normally as batch. Apart from that batch, you have 3 other dimensionalities. So the point is, if you want to get the output of conv, feed it to linear layer, you need to convert that into a vector. And you could do that with the view function, and if you pass -1, it decides on the dimensionality here, the size of that dimension. or you could explicitly say. So here you know that the output of your convolution is going to have this size, 16 number of features that you defined here by 5 by 5 height and width, and then I want to decide the dimensionality automatically. So you say if it is 10 images that are stacked together, that view function will decide on that, and that will be 10. And then you pass it into your linear function and you get the output. Now I'm having some internet issues here. It's becoming a bit slow. But anyway, so that's how to define a neural network in PyTorch. Two different functions that you need to have in order to tell your, in order to define your network. Say, what are the layers and what are the connections between those. And you could print that, you could see all the layers. You see that we defined the kernel size, default stride, and input output number of channels. A note here is that there are a few popular, commonly used pre-trained networks available on torchvision.models library. You could also use them by loading them by calling, for example, ResNet18. If you want, you could just call that. And if you want the network parameters to be pre-trained ones, these are pre-trained on ImageNet. You could use transfer learning and call this pre-trained true. By default, it's false, I think. So you need to pass that no matter which one of these you're using. The same pre-trained parameter can define whether you use pre-trained or not. And then you could, of course, print that and see all the layers and the connections. So ResNet is a very deep network. Another important note here is that all your networks, network parameters and your data should be on the same device. So here we don't have access to GPU. You could check if you have access to CUDA. CUDA is available, tells you if you have access to GPU, and then you could pass your data to GPU if you have. Okay, print devices CUDA 0. Okay, we probably have access to GPU here. So we have defined the data set, we have defined the network. The next important part is define the loss function and the optimization algorithm. For classification, we normally use cross-entropy loss, and optimization algorithm, you have a few different options. SGD, stochastic gradient descent, which was the original kind of gradient descent algorithm, and then there are more adaptive and complicated versions like Adam. Adam normally works well for most of the tasks data sets that you have. One thing that is common is that you need to pass all the parameters of your network as the first argument here to your optimization algorithm, so that the optimization algorithm knows which parameters it wants to train. And of course, learning rate is another common value. So these are normally 10 to the power of 3, -3, or -4 works well. Now you have defined your training data set, you have defined your network and loss function and optimizer. It's time to define your training loop. In your training loop, of course, you have multiple epochs in the sense that you load the same data but shuffled, and you load that multiple times and you train your network again and again on the same data. There are ways to decide when it's a good time to stop. For example, you could check, one thing that you should check most of the times, at the very least, is your performance on your training and validation set. So you need to constantly plot them and see whenever your training your validation performance is getting worse, that's probably the point to stop. So there are ways to control these hyperparameters, define them. That again is specific to task and data set. But the standard loop is that now that's an iterator. The train loader that we defined before, that's an iterator, in the sense that you could just do a for loop on that, and you would get the index of that data sample, which is batched already. If you remember, we defined the batch size of 4, and the data is a tuple of inputs and labels. So loop over the data, get the inputs and outputs separated, and make sure they are on the same device. Again, if your network is on GPU, your data should be on GPU, otherwise you cannot feed that into the network. The next most important thing is every time before you feed a sample into your network, you need to make sure that there's no gradients left on your parameters. So every time you need to calculate the gradients and do the back propagation, making sure that there's no gradients from previous steps. So optimize a zero grad, make sure that all the gradients are zero. Then you pass your inputs to your network, pass the network predictions and the ground truth labels to your loss function. And now you could call backward on this loss object. And what that does, it based on the architecture of your network, calculates all the gradients for every single parameter of your network and it stores them. One thing to note is that you have calculated the gradients here, but there's no training. No training has happened yet. And the training happens when you call this step. So now that all the gradients are calculated already, this step on the optimizer function uses the learning rate that you defined with that optimization from the algorithm that you defined and the gradients that you calculated and updates your parameters. So that's kind of a standard loop, and then you do that again and again on different batches of your data, and you do multiple debugs on your whole data set. And I think that's pretty much it for that's the general structure that you need for almost any deep learning kind of algorithm that uses classification. If you're using GANs, if you're using variational autoencoders, those are different stories, although the overall structure is the same in the sense that you need to define your data loader, you need to define your network loss function and the optimization, and you need to loop through the data. But how to do them, it depends on your task and data. Slightly, for example, I don't know, for GANs, for example, you want to pass your data, you get the output prediction, and then you want to pass your, for example, sometimes the ground truth that you have and get the output prediction, pass them to another network discriminator. So the way the pipeline slightly changes in the sense that how you feed your model and then what you do afterwards, but the overall main important kind of pieces that you need to have are the same. You could use Torch to save your network parameters. To get the parameters, you could call a static. This is way more important in deep learning because your training is not going to get a few seconds. Normally it takes at least a few minutes, if not hours or days. So it's very important to save them. You don't want to come back and train it every time. And we have some functionalities here to check the outputs of your network that I would leave them for yourself to try at your free time. There was one section left in terms of dimensionality reduction, but we probably need to skip that part as well. If anyone is interested, I will leave the slides and there are some code on the Jupyter notebook as well. We are a bit over time, but hopefully this has been helpful in getting you started with your methods, whether it is classical approaches or deep learning approaches. Is there any questions? Yes, of course, I will upload the notebook and the slides both for you to check and play, and of course the video recording as well. But it might take a few hours because the recording is on the cloud. So whenever it becomes available, I will share that. Any other questions? If not, thank you very much and see you next time.